anyway, I just wanted to talk about something completely random. Before I joined 47 Degrees, I was a researcher in an old life, and I want to talk about something which is kind of new. So we're all like functional programming, but functional programmers have this love-hate relationship with types, and people, like in the more Lispy languages, don't really use types that much. Then you have people like Haskellers, which are like super crazy about types. So, as I said, feel free to disagree with this slide. Maybe you use Lisp and you use types. Maybe you use Haskell and you don't use that. So, but there is this language called Agda, which is like a more powerful Haskell. And it's almost the same, except that whenever you use 2 colons in Haskell, you use 1 colon in Agda. And they came with this idea of having even more powerful types. And I wanted to tell you a bit about how it works and what's the new frontier they are working on. So you have types, normal types like natural numbers, and you should read this thing as a natural number is either 0 or another natural number plus 1. So like 1 is 0 plus 1, and 2 is 1 plus 1. And then you can define functions using pattern matching. So if you are not familiar with this syntax, that's how we write things in Haskell or in Agda for the sake of it. So we just sort of have a list of equations that define all the cases. So you can think of the plus function having a big case statement, a big match statement if you come from Scala, and then each of the cases come in a line. And then people came with this idea, if we want to define things like lists, we actually have like list of ints and list of booleans and list of whatever you want. So why don't we have list which may contain different types as elements? And in Agda, people use set instead of type for whatever reason. So you can write things like this. So you have a list which is either empty, or you can have a list which has a cons, which is one element and another list, and they have to agree on the same type A, and you get another list of type A. And then you can define things like appending 2 lists together. So you get 2 lists, and then you put them together in the usual way by recurring on the list. So all of this, I guess, should be more or less familiar to anybody doing functional programming, so how you append a list and how this list looks like. And then people went farther and thought, well, actually, it would be nice if my list also remember how long they are. Because then, if I try to get the first element of an empty list, the compiler should tell me, no, wait, your list has 0 elements. Just don't do that, please. I'm not going to allow you to do this because you will get an exceptions, and we don't like exceptions. So they came with this idea of indices in which you can put also like information about your data type in the type. So you can say, well, a vector, which is just another name for list, can either be empty, so that's the VNIL, and then you get a vector of 0 elements, or you can get an element A and a vector of n elements and get a vector of n plus 1 element. So if you put 1 element more to a list, you get 1 element more. And if you keep doing this, and you can do this in more powerful languages like Haskell or in Scala, you very fast come to the idea that when you define a function, sometimes you want to have functions also in your types. So if you have a vector of m elements and a vector of n elements, and you put them together, then you get a vector of m plus n elements. So you have exactly like all of them together. And the compiler is able to do this. Well, and as I said, in Haskell, you would use something similar called type families, but the idea is that sometimes you want your data types have information on it about the values inside. So let me go back for a minute. And so this is like what you have in mainstream languages, where mainstreams mean Haskell Scala. So just take it as mainstream as you want. You're free to decide about that. But let me go back and say, OK, now I have my natural numbers, and I want to have a data type for integers. And an integer is just like a natural number with a sign. So you can have plus whatever or minus whatever. So plus 1 or minus 1 or plus 2, things like this. But everybody knows that 0 has this special weird behavior that plus 0 and minus 0 should be like the same. It's like 0. There is no plus or minus in 0. But the problem is I can write functions which do not respect this invariant. I can write this wrong f, which sort of, to a positive number, give me number plus 1, and to a negative number gives me the number minus 1. So plus, like the absolute value is always increased plus 1, and the sign is kept the same. So I can write the function. It's there. But this function does not respect this idea that zeros are the same, because suddenly plus 0 gets mapped to plus 1, and minus 0 gets mapped to minus 1. And we just don't want that. And take this not as integer, but just some invariant of your data type, something that your data type should respect, but you cannot easily have in your data type. So people came with this idea of higher inductive types, hence the hit of the thing, which are like the next idea that hopefully will come to programming languages near to you in the future. So that's like how the research is looking. And what they came with this idea that when you define a data type, you can also state some things which should always hold, some invariants. So I'm saying here that my integers are plus or minus a natural number, and also, whatever you look at them, plus 0 should be treated exactly the same as minus 0. So now if you try to write this function, Agda complains, so the compiler complains. We don't, you know, what's the complaint? We don't really care. The point is that now we cannot define this function because plus 0 and minus 0 are treated unequally. If you try to define another function which actually works, like the absolute value, so absolute value of 0, it doesn't matter whether it's plus or minus 0, you will always get something. This actually works, and well, you define the function, and then you have to tell Agda how this equality is actually respected. So they came with this idea that you can talk about these equalities, and it's kind of weird, but you just say, well, my equality that I called at 0 is equal to set in both sides, so you should allow me to do this because I have just told you it doesn't matter whether I get plus 0 or minus 0, the result is going to be 0. And you can think, in this case, it's kind of easy. You know, the compiler should know it, but they had to do this because sometimes it's harder. So that's like the main idea I wanted to tell it for the Unconference. Like, they have this new idea of having data types. We have equalities and invariants. And if you think about it, you can have more examples, like if you define this kind of rows trees, which are like binary trees, but every level can have not only 2 children, but any amount of children. You can write this data type, which says like, OK, a leaf is just a tree with 1 element, and then a node is something which has n branches. But it could also have 0 branches, and we want to say somehow that a node with 0 branches should be the same as a leaf, because they actually represent the same idea. So if you try to do this right now, you have to be very careful of always respecting this invariant. But with this idea of higher inductive types, you can actually state this and say, look, a node with nil, with 0 children, should be exactly equal to a leaf. And then you can be sure that whatever you do respects this invariant, because the compiler will enforce it for you. And I have one extra slide that's only for mathematicians. Actually, all of this has some weird connection with topology and algebraic topology. So you can do things like proving that the product of 2 spheres is like a torus, whatever these things are. So I took this from the docs, but it looked cool. So you can do topology with these things. And well, that was it. So if you want to know more, so like if you want to know not about these types, but maybe the ones before them, you can actually check these tutorials and books about Agda and Idris, which are cool languages, which are like trying to push the frontiers of what we can do with types, and people have written about this. And then these higher inductive types are more like a research topic right now, but you can look for something called cubical Agda, which is like a fancy word, but it's all about this. Yeah, so thanks for listening. That was it. And yeah, let the Unconference begin.
Hello, everyone. I am Tomás Ruiz López. I am the technical lead of the iOS Swift team at 47 Degrees. And I'm here to talk about Swift, a programming language that is usually not present in functional programming conferences, and a project that I've been working for the last 2 years that tries to bridge that gap between functional programming and Swift. So, how many Swift developers are in the room? I can count 4, 5, not so many. How many at least know something about Swift or the features that it provides? Well, a little bit more. So, Swift is a programming language that was created by Apple and announced in 2014, so barely 5 years ago. And it is mainly used for iOS and macOS application development, but also can be used in backend with some additional frameworks. The language has rapidly evolved because it is open source, and the community is making a lot of proposals to improve it. And version 5.1 was released recently. And it includes many features that enable functional programming. For instance, we have higher order functions. That means that we can pass functions as parameters to other functions or return them as results of other functions. The language has built-in immutability with value semantics. That means that when we have value objects and we assign them, a new copy of that object is created instead of holding a new reference to the original value. The language also encourages a style of programming known as protocol-oriented programming, which is just a fancy name for something that is usually known in the functional programming community as programming with type classes and ad hoc polymorphism. And the language also lets you make types that you don't own conform to protocols that you have created. It supports algebraic data types via structs, tuples, and enums, and it provides pattern matching in order to work with some types. The type system includes optionals to work with potentially absent values, and a result data type to model success or failure in several operations. And these data types have combinators like map, flat map, or compact map mainly, that are also present in other types like sequences or collections. And finally, during the last WWDC before the summer, Apple announced Swift UI and Combine, which are two frameworks. The first one to do modeling of user interfaces in a declarative manner, and Combine is a framework for reactive programming. So even though Apple makes a huge effort not to mention the word functional or functional programming, both are a step closer to having a more functional usage of this language. So even though all these features already contribute to a very good environment to do functional programming in Swift, there are still some shortcomings. That is what we have been working on in Bow, which is a library for functional programming written entirely in Swift. So 2 years ago, I had no experience and no knowledge about functional programming. So I kind of went in the hardcore mode and started watching the videos of Bartosz Milewski about category theory. And I was inspired by the job that my colleagues were doing in Arrow for Kotlin. that, by the way, there are a couple of talks in the conference, and whatever you learn in those talks is equally valid in Bow and Swift, because we have designed it to maximize the compatibility between those two libraries. So what is inside Bow? Well, one of the features that the language is lacking is support for higher candidate types. There is a generics manifesto where Apple has stated that someday in the future the language may support higher candidate types, but there is no clear estimation on when that will happen. So meanwhile, we decided to take the results of this paper, Lightweight Higher Candidate Polymorphism by Jeremy Yallop and Leo White, and emulate them using the Swift type system. This emulation still has some limitations, and there is some boilerplate code involved in the emulation, but we are working towards keeping it to the minimum. So once we have higher candidate types, we can provide a set of type classes to work polymorphically with the data types that we create with this support. So we provide all the type classes in the functor hierarchy, together with many others, and then we provide packages for testing that verify the laws of these type classes. Instances for these type classes are provided for all the data types in the core module. So we have simple data types like ID, const, option, either, etc. We have types, modeling functions or Claisel functions. We have data types for collections, we have transformers, and all of them have been built with all this emulation for higher candidate types that we did. So what else we need for functional programming? Of course, we need to deal with effects and side effects. So recently we have launched version 0.6 of the library, and it includes a new module for effects. This module has a type class hierarchy for effects that is based on the work that my colleagues have been doing in Arrow, and the Scala folks have been doing in Cat's effects. We also include a bfunctor IO data type to suspend side effects, which lets us work explicitly with the error type. And we have included also an environmental effect type based on the work that CEO has done in Scala, that you can learn more in the workshop that John de Goos is giving later today. There are much more things. We have an optics module where we provide several optics using Barn-Larhoven encoding together with their polymorphic versions and type classes to work with them. And right now we are working on generating these optics for all your data types automatically so that you don't need to write them. In compile time, you can generate all the optics that you need. Streams. We don't have yet a stream module that we have written ourselves, but we have a very nice integration with the popular streaming library RX Swift, and probably we will have one for Combine, which is the standard streaming library that Apple provides. And what we did was just adapt this library to work with the emulation of higher candidate types that we did. And we have 3 more modules for free monads, recursion schemes, and generic programming that are not stable yet, but we would be expecting contributors to help us move these modules forward. So Bow has also originated some side projects, where the most popular one is Nef. Nef is a build tool similar to Anc for Kotlin or Tut for Scala, which lets us verify and compile our documentation and generate our website in continuous integration, all from a Swift playground. And there are many more cool features about Nef, and we will be announcing some new features soon. So I encourage you to go and check the GitHub project or the website, because it's really interesting. Besides NEF, we are working on 2 other side projects. The first one lets us generate network client from an OpenAPI specification using the bow effects module that we created. And the last one is bow meta, which is a library for meta programming that is what we are using to generate most of the boilerplate involved in some modules of the library. So this is a super quick overview of the library. There are many more things, from utilities to manipulate functions to an entire new syntax for monad comprehensions that we have developed. And I encourage you to go check out the website or the GitHub repo and try whatever new things you learn during the conference using Swift and Bow. And also, if you can help us make Bow more known by posting a tweet or starting the GitHub project, it means a lot to us. So if you have any questions, I will be very happy to answer them now, or feel free to approach me during the conference and we can have a chat. I would also like to thank all the team at 47 Degrees for helping me and giving me the resources to work on this project. Thanks.
Good morning, Cádiz. I'm going to talk about generic functional programming with type classes, and this is quite a heavy talk for the short time, but please bear with me. I'm Tapio Rautonen from Finland. I work for Umbra, and we do 3D optimization and all kinds of that. And if you are interested in our technology, please come talk to me later. But to the point, I'm going to pass the topic in reverse order to make any sense in this talk. And let's start with type classes. Type classes enable ad hoc polymorphisms, overloading without inheritance, and also they are sort of an interface that defines behavior and laws. I think type classes were introduced first in Haskell to provide equality and arithmetic operator overloading. And in Scala, which I'm going to use in these examples, we utilize traits and implicit context, which doesn't look that nice as in Scala, but they are still doable. So the simplest example of a type class, we have this equality, where you can compare two different things of the same type. And this is quite trivial, and here you have this Scala example of equality, where you compare A and B of types T. And how you implement this, and the idea is that in type classes you don't need to use inheritance or anything like that. If you have restricted types like string in Java or Scala or any other types that you cannot touch or inherit, you can still use type classes to do your own interfaces on top of those. And here we just have a simple example of having equality for double and also duration. And in the bottom you can see the example of using this. You can easily compare two doubles. You can say that are 1.3 and 1.2 equal. They are not. But 60 seconds and 1 minute are equal to each other. This is simple stuff. Then functional programming. This is what we are probably here all about. And in functional programming, it's a paradigm that concentrates on computing results rather than performing actions. And the key point is essentially referential transparency. So all expressions evaluate to the same result in any context. So there are no side effects, there are pure functions, and it relies on immutability, which means that the state can change after it's created. So, some examples. We have a simple add function here, add A to B, yes, very simple, same result in any context, no differences. And we can also sum a list of integers. If you have an empty list, it's 0, and then you just do a recursive sum of the all elements in the list. And this is also very pure, no side effects, and same result in any context. Then it all comes to the fact that if you have the result of A plus B, which is the AB, and add C plus D result to that, and compare that to the functional calls of adding A to B and adding C to D, these things must be the same thing. And if you are seeing typical programming examples below, you have a file where you read bytes, and then you compare the data, added the data, compared reading again some bytes from the file. And as you probably know this, when you read the file along, you get different bytes, so this doesn't hold and it's not referential transparent. And also, if you do the same with the atomic integer, which is thread safe holder for integers and adding and getting those values. And if you get a value from the holder and add those values together and then compare that to calling the increment and get 2 times again, and you probably realize that it's not the same again. So these things are not referential transparent and not very good for our purposes. Then in functional programming, function composition is a nice thing to have, and here we have subtract and multiply functions, simple stuff, and then we can compose things like creating a subtract1 function where we just call the subtract with a constant value, and also create a multiply 5 times where we just add a constant to the multiply function. And then we compose these functions again and create a mapping function for over a list where we first subtract 1 and then multiply the item 5 times and then call filter, which filters all odd numbers off. So the result is only 0, 10, and 20 out of that. And this is a nice thing to have with function composition. Then we have the generic part. And in generic, we think about generalizing code with type system assistance, for example, parametric types, generics like in Java, templates like in C++ and other languages. And then higher kind of types, like in the earlier talk, they were referred. They are basically just repetition of polymorphisms with the types, which means that we are just abstracting types with types. And we want to apply the principle of least power, which means that what is the simplest thing that does the logic that our business logic wants to do. So pick the simplest solution or interface or abstraction that solves your problem. And also the code is easy to change and interpret differently in the future. So we have the simple first order generalization here. We have a list of type T's and some interface for that. It's very basic. And then more generic version of adding things together, combining things together. We have the monoid type class, which was also referred in the earlier presentation, and we get a lot of help from the category theory when we think about generic functional programming. But in this case, we have a simple monoid here of type A, which basically defines how we combine different types. And here we can just combine type A with another type A and define a meaning for empty A. So what this means in practice, we have a monoid for integers. So basically this just means what does it take to add one integer to another. So we combine them with just a simple plus operator and then empty is 0. And then we can use that to create a combine all function that combines all values from list, and the type is A, and we define a constraint that this A must define the monoid type class. And here we just use a Scala, not so great syntax, but we go from value to value, starting from empty, and then combine all the values. So basically what we get is a sum of values or any kind of combination of the values, reducing it to only one value in the end. Then we are going to higher order function, higher order types. And this is monad, which is basically a container of f containing some other types. And in monad, we define flat map for the container, which defines what comes out of the container. There's another same type of container with another type in it. And then there's a pure value, which is basically a simplest representation of that container. And then with these two simple functions, we can define a more useful function map, which we have seen in the earlier examples a lot. But here we define map in generic way, so we can get any container, FA, and use a function from type A to type B, and then the result is the same container type containing the result B. And here we're just using Scala syntax again, using the implicitly helper to use flat map, and then pure with the function from the value which creates the value type B. Okay, then how we implement these. Here we have simple examples for list and a stream. They are different types, but kind of containers. We can think of them kind of containers. And we just use flat map for list and use the simple one value in a list as the pure function for that, and also pretty much the same thing for stream. And the result is we can now call map for lists and map for streams, which can be basically endless streams or whatever. But here we don't have to again change the actual implementation of a list or a stream. We can do all these things outside of the core types. And then we are going to tagless final, and we probably hear more about this or different way to do the same thing the next workshop from John de Goes, and he's probably more, quite a lot of more advanced in these things that I am, but I have a simple explanation of tagless final here. So utilizing all these patterns I explained earlier, we can create generic type assisted domain languages, and the name tagless final, I'm not actually sure where it comes from or how it should be defined, but here's some ideas. That tagless means that there is no need for runtime tag checking to perform type and error checking, and final means that the interpretation is done in the target monad and not deferred. And I'll show you some examples a bit later. And in the end, in tagless final, you define programs that are expressions that are just formed from operations which are just functions. And you can compare tagless final to free monad, and I think free monads didn't take that long because of their weird syntax they imply, but people are more familiar with the tagless final syntax because it looks like more traditional programming style. So in tagless final, here we define some algebra and business logic. We have a simple contact repository for container F and other type, which we define here for get method, which just gets some contact based on the name, and it might return contact or not. And then we have update, which updates some contact and returns that in a container. And then we create an address book, a simple address book interface, and we utilize the principle of least power here. What is the simplest thing we need to create an update address function? We have these two primitives like get and update, and how do we combine these? First we get by the name, and then we need to update the address with the another function. And here we can use the monad type class, which provides us the flat map and also the pure functions. And utilizing that, we have the most simplest implementation of update address without knowing any constraints or implementation details, like if we are doing this for futures, for IO monad or whatever. We don't need to understand how these things are implemented. We are just operating here with the simplest primitives that we can understand. So for that, then, when we have an abstract level of implementation, we can create the interpreters. Here I have a simple example of creating a future-based interpreter, which is just some kind of a database interface, getting the contact and then updating the contact. And then also an example of IO, which with an imaginary query interface, which returns the IO monad. So no matter what your implementation is, you have the core business logic with the most simple primitives and following the principle of least power and abstracted it all the way it comes to this. Then how do we use that? We just create a new address book with the interpreter and then call it. And why this is quite nice, for example, for testing or creating libraries or something that doesn't really care about the implementation, you can provide a nice library that just uses tagless final or another syntax to provide the core business logic for the library, and then you can have interpreters for different implementations, like if you are doing old school Scala, you can use futures, or if you are using catch effects, you can use IO monad and so on. So, all clear. Now we are all basically capable of doing generic functional programming with type classes, and I bet we get more of this in the Zio workshop soon. Thank you.
Let me introduce myself first. My name is Alfredo de Hoces. I work for The Workshop, a company in Malaga that specializes in gaming platforms for a variety of clients. And today I'm simply going to tell you the story of how we adopted functional programming, because during these couple of days a lot is going to be said in very, very technical, practical terms. But what does it mean for a company to adopt functional programming? What value does it provide? Is it difficult to adopt? How can you convince your product owners that you should really move to functional programming, or at least introduce it in some of your products? So it always starts with a problem. And yeah, the problem was one product that the company acquired. Then we formulated our hypothesis about functional programming. Then we got to it, we implemented a solution, and then the results, spoiler, were very good. It was very successful. And the problem was the poker product. So 3 years ago, our company acquired a product from another company, and it was already 10 years old. It was a multiplayer poker game. It was mostly based around C++. It had a little bit of everything, so there were a variety of technologies, but 90% of it was very old C++ code. And we had an aggressive product roadmap. So the product, they wanted to build a whole lot of new features on top of this. And we took a closer look at the architecture and the source code. and we found something similar to this. It was really bad. It was a set of basically single points of failure, Windows boxes, C++ code that was ancient, a spider web of sockets interexchanging binary messages. It wasn't easy. And we thought it was going to be very difficult, if not impossible, to build anything on top of it. So we got together, we thought, let's give it a push. Maybe we need to upgrade the technology here. And a few of us were already interested in functional programming. We got together, we proposed to the product, maybe we want to use Scala here. And obviously the first question was, how much money are we going to make with Scala? We said, well, I don't know. And what is functional programming going to give us? We said, well, it's very powerful. And the question was, how much money can we make with that power? So we had to kind of convince our product owners to move forward. So we got together, we did some brainstorming. Some of us were already interested in functional programming and knew a fair bit about it. Some others, we were kind of beginners. So we all got together and started talking, and we wanted to answer 3 questions. How can functional programming actually help us in our product? How does it translate to business value, and how can we actually seamlessly introduce it in our project? We couldn't just rewrite the whole thing and lock ourselves in a room for a year, so we had to find a creative solution here. And after considering a whole lot of things we liked, a whole lot of things we thought maybe were at risk or we're not clear about, we came up with 4 strong reasons to move forward to functional programming. First of all, immutability-oriented, the high level of abstraction it provides, the much easier way of handling parallelism, and then simpler and faster testing. So let's get into each one of these in a little bit more detail. The orientation to immutability. So our company, 80% of our products are built in Java, and we're all proficient, we like it, and we like the object-oriented programming. But normally with object-oriented programming, you will always have something like this. Your object, your properties, your methods, and this means one thing, shared mutable state, which is something not easy to avoid. It means you're going to have methods. Methods, by definition, have side effects, or else they'd be functions. But usually with functional programming, things are immutable, functions are pure, you give it a value, it gives you another value, and things don't change. And threads will not be accessing an object and trying to simultaneously change its value, which normally translates to incidents, weird, unexpected states, exceptions, etc. Obviously, you need side effects, because something without side effects doesn't do anything. It only calculates values, and we have a product to run, and we have a business to run. But what typically happens is that when you have an entire project based around OOP, you will end up having all the red dots that are instances of objects that will change state, will mute, will be accessed concurrently, they have side effects, they affect each other. And this, in the long run, it creates a little bit of trouble. So immutability tries to help here. There's this quote that says that shared mutable state is the root of all evil, and I actually agree, because we've seen it in our company a million times. What tends to happen when you have a project that's built around functional programming is that you will have a lot of green stuff here. These are functions, they calculate values, you get your data from your database, you can filter it, you can query it, and then there'll be a reduced set of functions or objects that actually create side effects. These are the ones doing input, output, right into a database, etc. Which means this whole thing is very easy to manage, and here you have to be a little bit more careful, but you don't have to be careful about the entire project. We also like the high level of abstraction it provides. So when we made the jump from imperative programming to object-oriented programming, you need a little bit of a change of your mindset. This is similar. So you're going to make a jump into something way more abstract, where you will have declarative functions where you declare your intentions rather than actually specifying how to do things step by step. The monad and functors, the higher order functions, the composition, all this gives us a lot of power, And we did like that. As per the easier parallelism, for us it means that if you have a lot of red, so a lot of shared mutable state and side effects, it is very difficult to parallelize. You will end up synchronizing bits of your code. You have to explicitly use threads. You have to fork them, join them. You need semaphores, etc. But when you have a lot of green stuff, so pure functions, side effect free, they're trivial to parallelize because they don't have side effects. There's nothing unexpected here. So here is just calculating the sum of 1,000 numbers in a parallel way. If you have 16 cores, they will be used just by using par. And then when it comes to simpler and faster testing, same principle applies. When you have a whole lot of interconnected objects that affect each other, if you want to test this one, you're going to have to set its state, mock the entire world around it, set the expectations on everything that might be affected. You will invoke some methods in here. You will have to check that everything around it actually behaved as expected. The expected calls were made. No unexpected side effects happened, and then validate its new state. That's the usual unit test with OOP. As opposed to functional programming, where you have a function, you give it a value, and if the result is what you want, then your test passes. And since most of your project is going to be like this, it means simpler, faster testing, which was a feature we liked. So our hypothesis, after considering all this, was that functional programming can help us develop powerful, performant, and safe software in a fraction of the time. It gives you power. You do more with less. It's less verbose. You need less code to achieve big functionalities. So this is what we went to the product owners with. And we told them that this will probably mean reduced development costs, less bugs and incidents, and increased performance, and a maximized reusability. So at the point they were convinced, we were convinced, and we got our hands to it. We chose a technology stack for our new functionalities. So the product wanted to build something on top of this, and the first deliverable was what we call the quick sit project. So players would choose tables, poker tables to sit at, and we wanted to change that into an automatic system to choose the best table for a player to play poker. So we decided to do it in Scala because it runs on the JVM. We didn't need new infrastructure. We already have all the pipelines. The only thing you do is just change the POM file and just specify you're going to be compiling Scala code, and then you get your jar files. So no radical infrastructure changes were needed. We reused our pipelines. We had monitoring in place for all our JVMs. And we have this Java compatibility that, in the end, we didn't use, but would have come handy. And we chose Agda because of the nice way that the actor model framework would suit our needs. It was a multiplayer poker game, and Agda is really good for concurrent distributed fault-tolerant systems, which we needed. It was real-time, money was involved, so we really wanted something powerful, safe. We could use streams and back pressure. We could interconnect different technologies, so if we had to intercommunicate one of the new components and one of the old components, we could probably maybe use Agda in the legacy bit and have them talk. So it all did suit the legacy architecture. And then we thought, well, we've chosen a technology stack. What the hell do we do now? How can we put this on top of our current product? And we used one principle, truth shall make you free, and one design pattern, which is my favorite, that's called wrap the crap. I absolutely recommend it. It's very, very, very useful. It saved our asses in this instance. So we have the legacy code. The first thing we did, so we want to be able to seat players automatically at specific tables. Which components actually knows which tables are already created in the system? That's when we search for the truth. That was the source of truth. That was the component we wanted to connect to. And then we went to wrapping the crap. Built a tiny little service around it, have an Agda actor connect a socket with it, and speak the old crappy protocol. So at that point, we had something that looked like a decent Agda microservice. And we built on top of it. How did we prepare? Some of us were interested, some of us knew a little bit of functional programming. We hadn't used it professionally ever. So What we did was first, we needed to understand functional programming principles. You don't just switch languages for the sake of switching languages. You really want to understand why you're making the step. So the people that were actually very clear on this principle explained that to the entire team. This is what we're looking for. Immutability, we want you to keep everything green as much as you can, reduce the side effects, etc. And we had literally 1 week Scala training for the newbies with Coursera courses by our beloved Martin Odersky. We read the Agda documentation, and people that were already proficient, they supported the rest of the team. And I'd say 2-3 weeks, we could actually get started, and we were proficient and kind of... Okay, so for the pain points, it wasn't all nice. It wasn't all rainbows and unicorns. Functional programming, it requires a mind shift. We were Java developers. We were thinking object-oriented at all times. We really had to get into this and think functionally. We had to make the best use of the immutability, of the power of the higher order functions. So staying pure, it takes an effort. You always had the tendency of introducing one tiny little side effect here and there. We actually had to be in control at all times, and it takes an effort. Actor paradigm is not trivial. It's really efficient. It was really great. It worked really good for us, but you really have to kind of get to understand what it's all about. So we need a lot of team support. We supported each other. We took it easy. We took it slow, and we built this in a safe sort of manner. Development. Squad of 5 developers, 4 sprints. We produced 2 new microservices, the crab wrapper and the API. 500 lines of Scala code. It was not a lot of code. We were surprised that we could actually create our first deliverable in just 500 lines. We had to fix one of the legacy components, so we had to get ourselves into the awful ancient C++ code and fix 10 lines, 10 new lines. We ran 2 load tests. We're impressed with the results. And then we created our first deliverable. We have our crappy component, our crab wrapper, a couple of microservices, an API, which we connected to the client. This used to talk to an API on the legacy bit, and we send it to the new service. And after the first 48 hours in production, what used to be 16 old nodes running at 75% CPU mostly at all times, they became 8 new components, basically sleeping through it. 5%, 7% CPU usage. No errors in the first 2 days, but the 10 lines fixing the legacy component created a memory leak, and the legacy component crashed, unfortunately. But everything that was new didn't really have a problem at all. So 1 month later, one small network-related incident with the Agda cluster. So there was something wrong with the network, and then the Agda cluster kind of disconnected, but that was it. No weird bugs, no strange accidents, nothing crashed. And the 16 legacy nodes were successfully decommissioned, so we reduced the blueprint by a great deal. And as of today, it's been 3 years, most of our deliverables to product are built on top of the new architecture. It means we unblocked an old, crappy legacy product that we couldn't build on top of, and we completely unblocked the product roadmap. So now we're able to deliver things rather quickly. Development is really fast and safe. We don't have a lot of issues. We don't get very crazy creating new things. It's easy for us. It's a great, enjoyable process. Once we're proficient in functional programming and Scala, we actually enjoy our jobs much more. Production incidents. We had a support team that was always on call, and we were always dealing with some weird calls, some player complaining, something crashed. Now that has been greatly reduced by the use of functional programming. We have successfully decommissioned 4 more components, and we are on our way to decommission a few more. And then our team size grew from 5 to 25. So we're all very happy about the transition. So conclusions, functional programming for us, it was really fun to learn, and once you understand its principles, it allows you to develop powerful software. There's an initial learning curve, yes, like with everything else, but it wasn't steep. It took us like 2-3 weeks to get started, and then it works. It does greatly reduce number of bugs and incidents, and it allows you to do much more with a lot less. So we made a bet, we advanced forward, and we're all very happy, and the product is happy about this. And it actually delivers a lot of value to our company. So that was our story. Thank you very much.
So first of all, who am I? My name is Flavio. Soy español. I'm Spanish. I don't look very Spanish, I know, but I promise I am, okay? So basically, I used to be a front-end guy. JavaScript used to be my shit, and now I'm joining in 2 weeks 47 Degrees, for which I'm very happy. So, slight change. Well, this talk was meant to be presented as what happens if you allow the creator of React to build a programming language. Is there any other front-end guys, people in the audience? Okay. Are there OCaml people as well? OCaml? Okay, a few of them. So basically, that's the creator of React, Jordan Walk. He works in Facebook, and he invented React and made the functional world come to life in the front end. So we're very thankful for him, for that. Sorry. Okay, so now he's working full-time in Reason in Facebook, and I'm going to explain why that is great. I have this meme. Whom of you have tried to do functional programming like in JavaScript? Okay, so functional programming is that beautiful fox to the left, but then you try to do that in JavaScript and it kind of falls short because you don't have a compiler to help you, you don't have really types, so you start to feel like that puppet miserable, okay? So what is ReasonML and what it comes into place? So basically, ReasonML is this, okay? I know we're in Cádiz. I know there are beautiful bridges in Cádiz, but this talk was completely improvised, so I gave this talk in London, okay? So basically, ReasonML is a bridge between the JavaScript world and its ecosystem and the OCaml world, in which you can leverage both ecosystems with a common language. You can interrupt Reason code with JavaScript, and also, as we're going to see later, there's a thing that allows you to write components in Reason and be reused in TypeScript and JavaScript. So that is very interesting. And also for OCaml people, it's basically it's the same language, but with a different syntax, and allows you to have all the powerful JavaScript ecosystem of NPM to the reach of your hand. Okay, so that is very powerful. A couple of things. I don't really have time to explain all this stuff, but basically speaking, all the mutable things in OCaml and Reason are have uglier syntax to prevent you from doing that. But if you want to do mutable or impure stuff, you can do it. So they removed things from JavaScript that are painful. For example, there's no null and undefined in Reason, just as in Haskell. They have the option type, which is just a maybe type in Haskell. So if null was the $1 billion mistake, I don't know how much is null plus undefined, okay? Also, we have true referential equality, value equality, which is something we don't have in JavaScript unless you use other libraries, and we have also immutable lists. If you want the JavaScript array, which is mutable, you need to use that weird syntax. It's a square bracket and a pipe. And if you want a singly linked list, the same list as in Haskell, but in Reason, you'd use the regular list with only brackets. Also, since, the var stupid thing in JavaScript doesn't exist in Reason, so there's no hoisting going on, fortunately. And since it's just OCaml, the const value, the bindings that you cannot change are called let. And if you want to mutate them, you need to use that kind of weird function syntax in which you say you want a reference, and then you can mutate that binding, okay? But by default, even though it's let, and we use let in JavaScript to mutate, in Reason it's const. It's immutable. So what else do we have in Reason? And what is like the bread and butter of Reason, and why the people is trying to learn it and move to it? Because we have ADTs. Yay! Well, it's kind of weird because they call it variants in Reason docs, but they basically sum types and product types, okay? So you define your state of your program. If you're doing React, for example, in Reason, which has first class bindings to it, the whole of your problems become modeling your state with the appropriate data type. So, for example, the state of my app I'm going to showcase later, it's either an error, or it's loading, or it is loaded and it has a root. And the root is another data type, which is the root for my application. And then I have actions. Any of you have done Redux with JavaScript? So basically, Redux is an attempt to do the Elm architecture and pattern matching in JavaScript, but in Reason we have pattern matching, so we don't need to try to fake it, we can actually do it. So these are my actions for my app, my example app, using ADTs. Blah, blah, blah. And then we also have record types, which is just, as in Haskell, syntactic sugar for product types. Also, things that are a bit weird to the beginning is that if you have a list of things or a type which wraps another type, it kind of looks like a syntax because the types in OCaml and Reason are lowercase, and we don't have the diamond syntax or the square bracket syntax as in Scala. So that is a list of comments. And also, since every file is a module in OCaml and in Reason, if you have a type that represents that module, or you have various modules in one file, the convention is to use that T to represent the type for the module, okay? So those are things that were very new for me when I came into Reason, but it's kind of a convention and everyone uses it. And then we get pattern matching for free in the language, which is absolutely awesome. This is an example of the routing application. When you need to do routing in your app, you have to use all kinds of crazy libraries in React.js just to be declarative. And in Reason, React is just a pattern match. You have your routes. You have destructuring because it's only like a pattern match for free. So there's no destructuring in Reason. It's just pattern matching. And then pattern matching looks like a switch on steroids. I think in Swift it's the same with the switch keyword. Yes, nice. There's also match in Scala. And then you can pattern match on values and on types. And if you don't care about some things, you can use wildcards also to discard them. You can also delegate parts of the pattern match or nest pattern matches and call other functions. We can pattern match also on the empty list, which is very interesting because since I come from JavaScript, I was doing list.length thingies, and that recurses the whole list every time. And my friend who was teaching me Reason told me, don't do this because you are in a functional language, and you can pattern match on the empty list, and this is O of 1. So it's way better. And my brain was like, okay. I know nothing about about this stuff, so it was very new to me. This is also very interesting. We can reuse pattern matches. I would like to know if this is possible to do in Haskell without language extensions. No, right? Okay. So this is one point in favor of OCaml, but it just saves you a couple of keystrokes. Also, since Reason is meant to be done for JavaScript people, they gave it syntax that looks like JavaScript, but it's not JavaScript underneath. So basically, the array operator, the REST array operator, how they call it, is basically head and tail. And the tail is for free. In JavaScript, there's allocation for every item of the new array because the spread operator creates a new array, and in Reason is another pattern match. It's pointless, so that is great. And also the default case is another wildcard. So for people who are new to pattern match, maybe this is not a great example. I tried to look to the best one possible, but I think it's kind of representative of the whole of it. So how does React in Reason look like? Well, it looks a bit like this. Since it's Facebook, the one who is doing it, they basically embedded JSX into the language. So it's an expression. And any of your pattern matches can return JSX, and they will be compiled eventually into DOM nodes, which is quite interesting. And we have to tell the Buckle script compiler, which is the compiler that translates OCaml code to JavaScript, that we want a very minimalistic React component in the end, just a function. That's why we have that weird annotation. And then in React, if you have done React, it's all about render functions. But in OCaml, they're called make. That's the default function from module. We have named arguments, which are awesome and do not exist in JavaScript yet. And also, we get for free JSX punning. So if the name of the property you want to pass to your component is the same as your binding, you can skip the whole post is equal to open key post of open key, which is very nice. It's called punning for JavaScript objects, but I don't know if it has other names. And also, everything is an expression in OCaml and Reason, so you don't use the keyword return. But there are very weird stuff going on here. For example, what is that arrow after posts? I'll try to explain it very quick. So basically, here I'm trying to look for a post in my list of posts, and okay, thank you. And I will try to show it. And if I cannot find it, I will show an error or nothing or an empty placeholder, and if I find it, I will show it. So what is this function? And what is this? Is this PHP? Are we back to PHP? No, don't freak out, I promise. So basically, list.getBy is the find function in JavaScript, but in JavaScript it's impure because it can either find the thing or return undefined, and you're screwed. And in Reason, it doesn't happen. It returns option type, which is the maybe type. So you have to pattern match on the none and on the some as well, which is awesome. Yeah, I had a demo to show, let me see, no, yes, okay, this is my demo, okay, it's what I build when I'm bored, just for fun, to try to learn. This is my cat and the Instagram API, but I don't have time to go into that, I'm sorry. And, well, the weird thing is the fast pipe. It's basically piping on the second argument. It's built like that for performance reasons. I don't have very much time to rush into this. You can do React hooks in Reason. I'm sorry. And I want to get to the very interesting part, which is there are effort being directed into, yes, doing Reason components and being interoperable to JavaScript and to TypeScript. So there's this library called GenType. You should definitely check this out because it makes interoperability awesomely easy. And also, since Reason works on the same AST as OCaml, you can leverage all the OCaml ecosystem and compile directly to native. This is a game built by Jared Forsyth, works in Khan Academy, that compiles to native iOS and native Android. It's a game of gravity. So that was pretty much it. Thanks, and see you in the conference.